Okay, so I want to introduce a principle that gives us insight into what happens when a reaction shifts from equilibrium. So, if we have a chemical reaction that is at equilibrium, right, meaning that the rate of the forward and reverse reaction are equal, and then we apply some stress to the system that throws it off, right, that throws its equilibrium off, the system will respond, the reaction will respond by shifting back towards equilibrium. And this is called Le Chatelier's principle. If we think about it, also just even from a, if we think about it just from a biological standpoint, right, which it's all connected, our bodies are naturally designed to achieve homeostasis, right? So when we apply some stress to our system, like when we're actually stressed out from exhaustion or whatever, our bodies naturally have a built in system to try to get back to equilibrium. So it makes sense, right? So if we are overheating, right? If we're working out and we're sweating and we're overheating, our body will sweat. It will actually do something to naturally try to cool us down. So it makes sense that if we go, this is what's true, we can think about on a macroscopic level, on a larger scale. So if we go even deeper within on a microscopic level in terms of chemical reactions that's happening in our body, we can basically think about Le Chatelier's principle as a foundational principle that explains why we see homeostasis happen, right, in our bodies. So the question that we're going to explore is what can cause stress to a system, right? System being a chemical reaction. If a chemical reaction is at equilibrium, what can basically disrupt that equilibrium? Now, just take a moment to think about it, right? A hint may be think about the things that we talked about within our kinetic section when we talked about different things that may change or impact the rate of a reaction, right? Because we're actually looking at the rate of our reaction and determining if it's at equilibrium. So that gives you an idea of what kinds of things may cause stress. So that's what we're going to focus on for the remainder of this section. So the first thing that we're going to talk about that can cause stress, our stressor number one, is a change in concentration. If we have a change in either the concentration of our reactants or our products, they will change the rate of our either our forward or our reverse reaction, right? And we saw that in kinetics. So that will also disrupt and change the equilibrium of the reaction as well. So let's look at an example. We have hydrogen and iodide combining to form hydrogen iodide. So if we were to write the rate law for this reaction, the rate of the forward reaction, as written going from reactants to products, is going to be equal to the rate constant K, and I just have these subscripts F to denote forward reaction, times the concentration of our reactants raised to some exponent, right? Because I haven't told you that this is a one-step elementary reaction, so we can't use the stoichiometry, right, to fill in these coefficients. So I'm just going to write a variable because we don't know what they are. But this is our rate law for the forward reaction. Our rate law for the reverse reaction, where we are basically just reversing our products and reactants, is K sub R, to stand for reverse, times hydrogen iodide raised to some coefficient. So these are our two rates for the forward and reverse reaction. We know that at equilibrium, both of these rates are equal. So if we change the concentration of either reactant, of hydrogen gas or iodide gas, and let's say that we increase the concentration. If we increase the concentration of either of these reactants or both, the rate of the forward reaction will increase. The rate of the forward reaction will increase. And so the rate of the forward reaction will then be greater than the rate of the reverse reaction, right? Starting at equilibrium, they're both equal. We add more reactants. Our forward reaction rate is going to increase in such a way where it now will be greater than the rate of the reverse reaction. Now, coming back to Q and K, right? Because we want to understand Q and K are the two constants that gives us information about equilibrium. So we want to compare Q and K to determine the direction the reaction will shift to reestablish equilibrium. So recall, this is our expression, our reaction quotient expression, concentration of products over reactants. So if our rate of our forward reaction becomes greater than that of the reverse reaction due to an increase in reactant concentrations, our reaction quotient will be less than K, right? And this makes sense. So if we just look at this expression from a mathematical standpoint, we've basically increased the number in our denominator because that's where our reactant concentrations are. So if we increase the number of our denominator, then our Q value will decrease. Our Q value will decrease. And we're always comparing at equilibrium, right? So Q is equal to K at equilibrium. We add more reactants, now our Q value decreases. So it's less than K. And remember from our previous example, if Q is less than K, meaning we have more reactants, our equilibrium will shift to the right. Our equilibrium will shift to the right. So taken together, if we increase concentration of reactants, our reaction quotient Q will decrease. And as a result, our equilibrium will shift to the right. The reason for this is because our rate of our forward reaction actually speeds up. It increases because we flooded the system with an increased concentration of reactants. Now you can think about the same, what if we were to decrease? If we were to decrease our concentration of reactants. So if we were to introduce something that ate up our reactants, then we would see the opposite, right? The rate of our forward reaction would end up being less than that of the reverse reaction. So our Q value would actually end up being greater than K because we'd actually decrease our denominator. So Q would increase. All right, I'm going to pause